So in 30-1, we learned about the unit circle. It can be used to find the exact values of sine, cosine, tan, as well as the reciprocal ratios of certain angles. And those angles were essentially multiples of 45 degrees or multiple of 30 degrees, multiples of pi on 4 radians or pi on 6 radians. And they are derived from some special triangles. The first one came from a unit square where each side is 1 unit long, and then a diagonal is drawn in there, which bisects the angles at the top and bottom left. It also creates a right triangle. It doesn't matter whether you use the bottom right triangle or the top left, the values will be the same. The hypotenuse can be found by using Pythagorean theorem. So c squared will equal 2 and c will equal root 2. And so from this we can state the sine of 45 degrees, which is pi on 4 radians. That is 1 over root 2. And if we rationalize that, it will be root 2 over 2. The cosine will be the same value because the adjacent side is also 1. So that's also root 2 over 2. And the tangent of 45, or pi on 4 radians, is 1 over 1, opposite over adjacent. And so this allows us to fill in some of the coordinates on the unit circle. The unit circle is drawn in standard position, which means the initial arm is on the positive x-axis. And when we build it, we go in a positive direction, which is counterclockwise. So it's 90 degrees at the top, 180 degrees to the left, 270 degrees at the bottom, and then back at 360 degrees. But that's in terms of degrees. We can also do this in terms of radians. 90 degrees is pi on 2 radians. So every 90 degrees is another pi on 2. So the next one will be pi, which is 2 pi on 2, 3 pi on 2, and 4 pi on 2, which is 2 pi. And then 45 degrees, which is the angles that we just found, is there. And we can go around the circle in terms of 45. Another 45 is 90. Another 45 is 135 degrees. Another 45 is 180. Then 225 degrees. Then 270. Another 45 is 315 degrees. And then 360 degrees. And we can go around in terms of radians. Each 45 degrees is another pi on 4 radians. So there's 1 pi on 4. 2 pi on 4 is the same as pi on 2. Then we'll have 3 pi on 4. And actually, let's move these inside. Another pi on 4 would be 4 pi on 4, which is pi. Another pi on 4 would be 5 pi on 4. Then 6 pi on 4, which is 3 pi on 2. 7 pi on 4. And then 8 pi on 4 is back to 2 pi. And we've seen above that the sine and cosine of 45 degrees or pi on 4 radians is root 2 over 2. We also learned that at each point on the unit circle, you're going to get an x and a y component, and they are in the order cos theta, comma, sine theta. The first number at the point is the cosine, the second number is the sine. So we can start by labeling the multiples of 90 degrees, because the unit circle is a circle with a radius of 1. And this tells us what the cosine of each of these angles is, as well as the sine of each angle. The first number is the cosine of that angle, the second number is the sine. And now we can fill in at 45 degrees, they're both root 2 over 2. And at 135, which is 3 pi on 4, it's the same two numbers, just with the appropriate sign. Because you're going left from the origin, x is negative, y is positive, because you're going upwards. This tells us that the cosine is negative in that quadrant, the sine is positive. Down here at 225 or 5 pi on 4, they're both negative. And at 7 pi on 4, it's positive negative. And we saw the tangent was 1. We got it from that special triangle going opposite over adjacent, but we can also get it from the sine and cos, because we know that tan theta equals sine theta over cos theta. Either way, the sine divided by the cos will either be 1 or negative 1, depending on whether sine and cos are positive or negative. So in the third quadrant, that should have been positive 1, because they're both negative. And if we go and fill in the tangent at the multiples of 90, remember it's sine over cos, so at 0, it's 0 divided by 1, which is 0. But up at pi on 2 or 90 degrees, it's 1 divided by 0, which is undefined. Doesn't exist. At 180, it's 0 over negative 1, which is 0. At 270, it's negative 1 over 0, which again doesn't exist. So then we use the second special triangle, where each side was 2 units long initially. And because it's an equilateral triangle, all the angles are 60 degrees. But then we drop the perpendicular bisector. So it's perpendicular to the base and it bisects it. So now that side is 1, that side is 1. It also bisects the angle at the top. Each one is 30 degrees. We've got the base of the triangle to be 1. We've got the hypotenuse to be 2. We can find the height of the triangle using Pythagorean theorem. It'll be 2 squared minus 1 squared. 4 minus 1 is 3. And then 8 would be the root of 3. And now we can get the sine, cos, and tan of both 30 and 60 degrees. So let's go back to our unit circle. This first stop is pi on 6 radians, which is 30 degrees. So from 30 degrees, cosine, which is our first one, is adjacent over hypotenuse, root 3 over 2. The sine is opposite over hypotenuse, which is 1 over 2. And if we get the cosine, remember cosine is opposite over, the tangent I meant to say, is opposite over adjacent. That's 1 over root 3, or root 3 over 3, if you rationalize. So every stop on here that has a denominator of 6 will be another spot where we'll have those same two numbers. All that'll change is whether the values are positive or negative. So this stop down here, this will be 5 pi on 6. It's 1 pi on 6 short of pi. which is 6 pi on 6. And again, our values will be the same. The only thing that will change is whether it's positive or negative. So the x value is negative root 3 over 2. The y value is positive 1/2. So pi is 6 pi on 6. Another one is 7 pi on 6. And it's going to be both negative. And then the last one here will be 11 pi on 6, where it's positive negative. And we can also put our angles in degrees here. Right, that was 30. This would be 150 because it's 30 degrees short of 180. 210 because it's 30 degrees past 180. And this last one is 30 degrees short of 360. So that's 330 degrees. And the last one is 60 degrees, or pi on 3 radians. And if we go back to the special triangle, remembering that the first number is the cosine adjacent over hypotenuse from 60 degrees, that'll be 1/2. Sine is opposite over adjacent, that'll be root 3 over 2. And the tangent is 60, is opposite over adjacent, that'll be root 3 over 1, or just root 3. Another 60 degrees takes us to 120 degrees, or 2 pi on 3s. If we fill in the other ones, then we'll go back and put our coordinates in. This stop here is 60 degrees past 180, that's 240 degrees. Again, 180, or pi radians, would be 3 pi on 3. Another one will be 4 pi on 3. Another one will be 5 pi on 3, which is 60 degrees past 240, or 300 degrees. And again, the coordinates here will be the same as at 60 degrees, except for changing signs. This will be negative 1/2, comma, root 3 over 2. Down here, they're both negative. And in the fourth quadrant, it's positive negative. And the tangent of 60 degrees, we said, was root 3. So all that'll change in the other quadrants is whether it's positive or negative. So that's negative root 3. Down here, it's positive root 3 and negative root 3. I've got to go back and fill in the pi on 6's. The tangent of pi on 6 is root 3 over 3. In the second quadrant, it will be negative root 3 over 3. In the third quadrant, positive root 3 over 3. And in the fourth, negative. Okay, so there's the entire unit circle labeled. And we learned that you only actually have to remember the first quadrant, because you can use the cast rule and reference angles no matter what quadrant you're in. And we also learned about that hand trick, right? So this is bottom hand, or bottom finger is 0. That's pi on 6, pi on 4, pi on 3, and pi on 2, or 90 degrees, right? At the first stop, which is pi on 6, or 30 degrees, if you put that down, it'll be the root of this many fingers for the sine, root of 1 over 2. which is 1/2. That's the sine. The cosine is the root of this many fingers, √3/2. Remember, cosine comes first. At pi on 4, it's the root of this many fingers, √2/2, comma, √2/2. And at pi on 3, it's the root of this many fingers, which is the sine, the root of this many fingers over 2, which is the cosine. So you can remember that hand trick as well to get those coordinates in the first quadrant. So we can use them to evaluate each of the following as an exact value. The first one says the cosine of pi on 4 plus the sine of pi on 4. From the unit circle at pi on 4, both the cosine and the sine are √2/2. So those have a common denominator, so you can add them together by adding the top together and keeping the same denominator. And then the 2's cancel, so we're just left with √2. There's the exact value. And often when you see that word exact value, that's what it means. Use the unit circle. For question 2, we want the cosecant of pi on 3 minus 3 times the cotan of pi on 6. So if we go to pi on 3 on the unit circle, that's the same as 60 degrees. We want the cosecant, which is the reciprocal of sine. The sine is √3/2. So the cosecant will be 2/√3 minus 3 times the cotan of pi on 6. So back to the unit circle. The tan of pi on 6 is √3/3. But remember, that came from 1/√3. That's where it came from. And if you think of it as 1/√3, then the cotan is just √3/1 or √3. So now we will just simplify this. We'll get a common denominator of √3, which means you're going to have 2 minus, right? The first term already has a denominator of √3. The second one, the denominator is actually 1 right now. So we'll get it to be √3 by multiplying top and bottom by √3. And √3 times √3 is 3, times 3 is 9. So it becomes 2 minus 9, which is -7 over √3, which again we would rationalize by multiplying top and bottom by √3. So there's the exact value for number 2. And you can always check these on a calculator. We found our answer to be -7 √3 divided by 3. It's that value there. So what we'll do is we'll put the original expression in our calculator. Because those angles are in radians, we have to be in radian mode. And to get the cosecant, because there's no cosecant button, we'll use brackets and go 1 divided by the sine of pi on 3. Minus 3 times the cotan of pi on 6, which in brackets is 1 divided by the tan of pi on 6. So if you hit enter, you get exactly the same decimal that we got. It tells us that our answer is correct. The difference is, though, that the calculator gives it as an irrational number, where the unit circle gives it to us as an exact value. Right, but we can still use the calculator to check our answer. Looking at number 3, we want the secant squared of 60, which is the secant of 60 all squared minus the sine of 30 degrees all squared. So back to the unit circle we go. At 60 degrees, we want the secant, which is the reciprocal of cosine. The cosine is 1/2. So the secant will be the reciprocal 2/1. But that needs to be squared. 2/1 or 2 squared minus the sine of 30 degrees. Remember, sine is the y value. At 30 degrees, the y value is a half, and that needs to be squared as well. So it'll be 4 minus 1/4. And if we get a common denominator of 4, it'll be 16/4 minus 1/4, which is 15/4, 3.75, which we can check on our calculator. Now, though, we have to be in degree mode because our angles are in degrees. To do the secant of 60 all squared, we'll have to go in brackets 1 divided by the cosine of 60. Close the bracket on the 60, close the bracket on the expression, and then square it. Minus, in brackets, the sine of 30 degrees, all squared. Gives us 3.75, which is what 15/4 is. Okay, so it checks. Number 4, the sine of pi on 3, which if you look on the unit circle is root 3 over 2, times the cosine of pi on 6, which is also root 3 over 2, plus the secant of pi on 4. Well, secant is reciprocal of cosine. Remember, the cosine was originally 1 over root 2. So when you take the reciprocal of that, you'll just get root 2. Same thing with the cosecant of pi on 4. That's the reciprocal of sine, but the sine was also 1 over root 2. So the reciprocal is root 2 over 1. So when we multiply these out, you're going to get 3 over 4 plus 2. A common denominator of 4 will give us 3 plus 8 all over 4, or 11 over 4. 11 over 4 is 2 3/4, which we can check on our calculator by changing our mode to radians. So we'll have the sine of pi on 3 times the cosine of pi on 6 plus, for the secant of pi on 4, we'll have to go 1 over the cosine of pi on 4. Close the bracket on the pi on 4, close the bracket on the 1 over cos pi on 4, as well as the cosecant, which is 1 over the sine of pi on 4. So that's all in there, and we get the same answer, 2.75. We also spent a bit of time looking at the graphs of trig functions and transformations of them. Remember that for sine and cos, we had critical points at every pi on 2. So 1 pi on 2, 2 pi on 2 is pi, 3 pi on 2, 4 pi on 2 is 2 pi. We saw that the graph of sine went up to 1 and down to -1. It started in the middle, and every pi on 2 you had another critical point, which took us to a maximum, back to the middle, a minimum, back to the middle. So there's one cycle of the graph of sine theta. It's a curve. Cosine was very similar. It also had critical points at every pi on 2 or 90 degrees. Same max value and min value. The difference was that cosine started at the maximum. And then the next critical point is the middle, minimum, middle, back to the maximum. So some of the characteristics of these graphs that we talked about was that the graph of sine and cos both have an amplitude of 1. Remember, the amplitude is the distance from the middle to the max or the middle to the minimum. The domain of these graphs were both all real numbers. There were no restrictions on what you can take the sine or cos of. We just graphed one cycle of the graph, but the pattern continues forever in both directions. The range of these two graphs are the same. They go from -1 to +1, which are both included, hence we use the square brackets. Our x-intercepts for sine are every multiple of pi. Zero pi, 1 pi, 2 pi, -1 pi, -2 pi, every multiple of pi. But for the cosine, it's a little bit different. It starts at 90 degrees and then goes every multiple of 180 degrees after that. Okay? So those are some of the characteristics that we talked about. We saw that the graph of tangent was completely different. It did have critical points at every 90 degrees or pi on 2 radians. But one of the biggest differences is that these graphs have no amplitude, but they do have vertical asymptotes. The first asymptote was at 90 degrees because the tangent of 90 didn't exist, it's undefined. Same thing at 270 degrees. The tan of 270 doesn't exist, it's undefined. This graph does go through 0, 0. And this is what it looks like. The one thing we didn't mention for the graph of sine and cos is what the period is. The period is how long it takes to go through one cycle. And for sine and cos, that is 360 degrees, or 2 pi radians. Tangent is different. There is no amplitude, because the graph extends upwards forever as it approaches the asymptote from the left, downwards forever as it approaches the asymptote from the right. Our domain is different because we have non-permissive values. The domain would be that x cannot equal 90 degrees and every multiple of 180 after that. The range goes downwards and upwards forever. So again, lots of differences between tangent graph compared to the other two. Our x-intercepts are every multiple of 180 degrees. And the other thing that's different is that the period is only pi radians. Every pi radians, it goes through one cycle. We can also graph the reciprocal ratios. So you're still going to have critical points at every pi on 2 radians, or every 90 degrees. Cosecant is the reciprocal of sine. If we look back at the sine graph, we've got some key points here. 0, 0. The y value is 0. Then 0, 1, 0, 0, 0, -1, 0, 0. So if we take those initial points, to get the corresponding points on the graph of cosecant, you're going to take the reciprocal of the y value. So for cosecant, the first point will be 0, instead of 0 over 1, it'll be 1 over 0, which doesn't exist. It's undefined. So you're going to have a vertical asymptote where x is 0. At 0, 1, that's 1 over 1. Well, the reciprocal will also be 1 over 1. So that'll be the point 0, 1. Back at 0, 0, again, the y value will not exist. It's undefined. So you're going to have a vertical asymptote there. At 0, -1, the y value is -1. -1 over 1 becomes 0 over -1, which is -1. And once again, 0, 0, the y value will not exist. So again, we're going to have a vertical asymptote here at x is 0, x is pi, and x is 2 pi. That's where all these points are, where the reciprocal ratio is undefined. At 0, 1, that was at pi on 2, the y value is still 1. So let's put those on there. There's 1, there's -1. So that'll be that point. At 3 pi on 2, that's where it's -1. Right there. Now we could take some other points on, let's say, the unit circle. For example, if we took pi on 6 radians, which is about right there, cosecant is the reciprocal of sine. The sine is 1/2. So the cosecant will be 2 over 1, or 2. So that'll be this point up here. Same thing at pi on 3 radians. The sine is √3 over 2. The reciprocal will be 2 over √3, which is positive. Right, that's pi on 3 radians, and the sine there is √3 over 2. So the reciprocal will be 2 over √3. Whoops. 2 divided by √3. Again, it's greater than 1, 1.5. So this point here will be, somewhere over there. And we could get more points if we wanted to, but what this shows us is that this part of the graph would look like that. And the other part of the graph would just go downwards, approaching the asymptotes. So there's the graph of cosecant theta, the reciprocal of sine. So in the same way, we could graph secant, which again has critical points at every 90 degrees, or pi on 2 radians. And in the same way, we could graph this, only now the asymptotes are at 90 degrees. The shape, though, will be the same. And again, I showed you how we can get the points just by taking the points on the unit circle and doing the reciprocal. Whoops, that's a little bit off because it should start at 1 and go up. This one goes -1 and down. And then at 360, it'll be just the left side of the U. And then finally for cotan, remember tangent had asymptotes at every pi on 2 radians. Cotan will have asymptotes at every pi radians, or every (180) and every multiple of 180 after that. And it's going to be like the reverse of the tangent graph, because it's the reciprocal. So that's what that one will look like. So those are our base graphs. So the reciprocal graphs are new. We didn't look at those in 30-1. But again, I showed you for cosecant how we can get that by taking points on the sine graph, taking the y values, and reciprocating them. You can get them that way. So we saw that they can be transformed using that general equation. Remember, A causes a vertical stretch by a factor of A, and when A is negative, there's a reflection about the x-axis. B causes a horizontal stretch, but that stretch factor is 1 over B. The period is 2 pi over B for sine and cos, pi over B for tangent. Also, our critical points are at every pi on 2 times 1 over B. C causes a horizontal shift. When C is negative, it goes to the left. When C is positive, it goes to the right. But remember that the C value is the opposite of what it appears to be, because the general equation is theta minus C. You put a positive value in for C, which means the graph goes to the right, it stays theta minus. But you put a negative value in for C, which means the graph goes to the left, and there the minus becomes a plus positive. So the value of C is the opposite of what it appears to be. D shifts the graph up and down. When it's positive, it goes up. When it's negative, it goes down. So we're asked to graph these 3 functions, cos theta, 3 cos theta, and cos 3 theta between 0 and 0 and 2 pi. So that's pi, 2 pi, that will be pi over 2 and 3 pi over 2. Goes up to 1 and down to -1. So we start with the graph of cosine theta, which remember starts at the maximum. Critical points at every pi on 2. So this is our base graph for y equals cos theta. Now for the next one, it's 3 cos theta. So I'm just going to have to expand my y-axis here. So there's 2, 3 is about there. -2, -3. So for 3 cos theta, that means a vertical stretch by a factor of 3. And starting at 0, 1, instead of starting there, it's going to start at 0, +3. your critical points are still every pi on 2. There's been no change horizontally. The change is vertical. All the y values are multiplied by 3. And the x-intercept, where y is 0, stays invariant because 0 times anything is 0. Right, so there's the graph of 3 cos theta. And then finally for cos 3 theta, that is a b value of 3, which means a horizontal stretch by a third. So everything horizontally is stretched by a factor of 1/3. Instead of having critical points at every pi on 2, it's going to be 1/3 of that, which is every pi on 6. So on the scale that we have on the x-axis of pi on 2, that's the same as 3 pi on 6s. So we're going to divide the distance between 0 and pi on 2 into thirds. There's 1 pi on 6, 2 pi on 6, 3 pi on 6. Same as pi on 2. 4, 5, 6 pi on 6. 7, 8, 9 pi on 6. 10, 11, 12 pi on 6. So our amplitude hasn't changed. It's changed horizontally. We're still going to start at our maximum, but our next critical point is pi on 6. And that's where we're in the middle. The next one, you're at a minimum. The next one, you're at the middle. And the last one, you're at the maximum. Right? That is at 4 pi on 6. That is the end of the first cycle. That should be the distance for one period. And remember, the period for tangent is normally pi radians, but that's multiplied by 1/3. So that'll be pi on 3 radians. I'm sorry, 2 pi. 2 pi over 3, which is 4 pi on 6. Right? For sine and cos, the period is 2 pi. So that gives us a period of 2 pi on 3, which is 4 pi on 6s, and that's where we ended here. So we'll just continue the same pattern. Every critical point will be another pi on 6. And when we're done here, we should have 3 complete cycles in 2 pi, which we do. So there's our first cycle, our second cycle, and there's the end of our third cycle. And there's the graph of y equals cos 3 theta. So now we want to do some transformations of sine theta between negative 2 pi and positive 2 pi. So we'll say that's negative pi, negative 2 pi, positive 2 pi. So that'll be negative pi on 2, negative 3 pi on 2. And we'll start with the graph of sine theta, which goes up to 1 and down to -1. Sine theta starts in the middle, critical points at every pi on 2. End of the first cycle is at 2 pi. Going backwards, follow the same pattern. So there's the graph of sine theta between -2 pi and +2 pi. Sine theta starts in the middle. Now, for y equals sine of theta minus pi on 2, that'll be a phase shift of pi on 2 to the right. Our value of c is positive pi on 2. Remember, it's always the opposite of what it appears to be because the general equation is theta minus c. So this graph will shift pi on 2 to the right. Every point will go pi on 2 to the right. Every point. So that's what I'm doing here. I'm taking every point and shifting it pi on 2 to the right. This one here is over there. And if we go back to the start here, to finish it off to the left, there's that graph. And then the last one we're asked to do is for theta plus, negative sine theta plus pi on 2. Two things are going to happen. The graph will reflect over the x-axis because a is negative. And it'll also shift. We'll have a phase shift of pi on 2 to the left because c is negative pi on 2. You must put a negative value in for c, and then the minus minus becomes a plus positive. Remember, we always do our stretches and reflections first, our shifting last. So the x-intercepts of the original graph, when you reflect over the x-axis, won't change, but the graph does shift pi over 2 to the right. So let's take this negative pi. When you reflect it over the x-axis, that doesn't change, but it must go pi over 2 to the left. So I'm going to start with the x-intercepts first. So that one there, 0, 0, doesn't change after the reflection, but then it goes pi over 2 to the left. This x-intercept at pi on the original graph doesn't change after the reflection, but it has to go pi over 2 to the left. Same thing with the 2 pi. That point where y is 0 doesn't change after reflection, but it must go pi over 2 to the left. So let's take this maximum. When you reflect it over the x-axis, it becomes a minimum, and then it goes pi over 2 to the left. It'll be that point down there. This minimum at negative pi on 2, when you reflect it, becomes a maximum, and then it goes pi on 2 to the left. So we're going to see here that the graph of negative sine theta plus pi on 2 is the same as the graph of theta sine of theta minus pi on 2. It gives us the same graph. So this is also the graph of y equals negative sine theta plus pi on 2. And obviously sometimes that'll happen. sometimes that'll happen. So for this last one, we're doing reflections of, we're starting with our base graph of tan x. So we weren't asked to graph it, but it just makes sense to start with that as our base graph between 0 and 2 pi. So that will be pi, 2 pi, pi over 2, 3 pi over 2. And the original graph had asymptotes at every pi on 2. So this is the graph of tan x. Now, for y equals tan 2x, that's a b-value of 2, which is going to cause a horizontal stretch. And it's about the y-axis. By a factor of a half. So everything will be half of what it was before. So instead of having asymptotes at every pi on 2, the first one will be half of that, which is pi on 4. So there's our first asymptote. Now the asymptotes for tangent are pi radians apart, because that's the period. This one here will be pi over 2 radians apart. So if we start at pi on 4, which is, and we add another pi on 2 onto that, pi on 2 is 2 pi on 4. So again, what I'm talking about is I'm talking about the period here. So let's write this out. The period for this graph will be every pi on 2. If the first asymptote is at pi on 4, our next one will be pi on 2 away from that. So to add those together, we need a common denominator. And pi on 2 would be 2 pi on 4. So the next asymptote will be 3 pi on 4, which is halfway between 2 pi on 4, which is pi on 2, and 4 pi on 4, which is pi. And I can continue that pattern on. This is where all the asymptotes are for that graph. And so this will be the new graph. So that is the graph for tan 2x. And then for negative tan 2x, the graph will just be reflected over the x-axis. So in black is negative tan 2x. It's just reflected over the x-axis. And so it would look something like that. Okay. So most of this is review from what you learned in 30-1. The only difference part that we've added here is we looked at the graph of the reciprocal ratios, and we did a bit more work with transformations of tangent. The rest of the stuff you had done before. So for practice, you can work on these questions.